Alright, I just wanted to do that quick review of a Mohr's circle. So, really, what Mohr's circle is doing is it's taking a stress element. I know we typically look at a 2D stress element, but really, Mohr's circle is essentially a three dimensional stress element when you look at it and apply it as such. So, there's really um, three, three normal stresses you have: sigma x, sigma y, and sigma z. And this is going to give us basically really three potential normal stresses, unless we say one of them is zero, which we have essentially done for the homework. Um, so really, a lot of these problems have been simplified to doing it on an axis where it's similar to, we have a zero stress at all times. So in this case, z is our zero stress. They say just assume any components not shown are zero. So what we're doing for this problem is really a simplified stress problem. And when you go through and do it, what you would be doing, so we would have, for problem one, for instance, we have our Mohr's circle. We would go through the steps here that are laid out. Mott does a pretty good job in laying out these descriptions and procedures and working through these stress elements. And so what you would end up doing is you'd perform the stress analysis to determine the magnitudes and direction of the normal stresses for normal stresses and shears. And this is done when you do a typical stress analysis for an actual problem. And they show that here in the book as an example. So really the book does a really good job in laying out an example problem where they walk through and they do the stress analysis, they do the statics, they figure out our R and A values, our reactions at A and D. And then we look for where our maximum stresses would be located. This would be at our maximum moment, right? And we have a rather large stress. We have a rather large moment. This is where our maximum stress is going to be located. So we want to analyze this stress element, and we want to basically figure out what our maximum stresses are in really the three-dimensional stress plane. In this case, we could say on the surface of this drive shaft here, or this shaft that we're translating energy over. So we have two belts that are one's driving another, and we end up having this bending stress. So as you might expect when you have stresses like this, we have two forces pulling in one direction. We're going to get this bending, right? So we see this bending. Found a piece of styrofoam, figured it'd show a good example. So we end up getting stresses like this. So we end up getting compression in the bottom, tension in the surface here, right? So we get this bending stress, and this is really what's causing this tension. So we're looking at tension in this case, and we want to look at our maximum bending in that tension, and we're going to go through and essentially look for that tension as our normal stress, and the shear is due to the torque in the bar. So they go through and they analyze it, and they get sigma x by taking that moment, dividing it by your shear modulus, or your modulus, cross-sectional modulus, and then they look for this one here, max shear, or shear xy is going to be your torque divided by your z polar moment of inertia, and that gives you your stress element. In this case, we're going to assume stress going in and out of the beam is zero, so there's no stresses being applied to the beam. And that's really how you would go through and do really step one, perform that stress analysis. So you need to make sure you have obviously the stresses to apply it. And this is where we get our sigma x, our sigma y, and our tau xy. In this case, again, that sigma z value We do have one, but it's just going to be 0. We're assuming this is 0. Right. So that's really step 1. Step 2 would be draw the stress element. So we have the, go back to the problem, we have sigma x is equal to 20 KSI, sigma y is equal to 0 KSI, and tau xy shear is 10 KSI. So we have that. We want to draw our stress element. So in this case, we draw our stress element to that square, that value that we picked and said that's the location that we're going to have stress, and we want to look at that max stress there. So in this case, we said we have a tension. It says 20 KSI. It's positive, right? So we know it's a tension. If it's negative, it's a compression. So sigma x is equal to 20 KSI. Our shear, in this case, if we have a positive shear, we have positive 10 KSI. Positive shear is in clockwise direction, so it's opposite of right hand rule. And we have that for our x axis would be positive. So it would be positive, and then obviously we have to have a counteracting shear. So our shear in this case, tau xy, is positive 10 KSI. And over here for tau yx, so really our y-axis, right? Sigma y we said was 0. But sigma yx is our negative 10 KSI. That's our counteracting force to this shear here. And again, these are equal and opposite, right? So we have sigma y, sigma x acting equally in the opposite direction. So that's our stress element. That's our main stress element that we're looking at. And now we want to look at what would our stress element look like in the maximum principal stresses, so maximum of our normal stresses here. And what would it look like with our shear at the maximum angle? So we want to figure out, all right, well, in what orientation would this cube be? Would it have the maximum principal and maximum shear stresses? And the nice thing about Mohr's circle is that it shows that visually. So if we work through the problem, and they show a decent number of examples here, but so hopefully it gives you a few to kind of look over. Following the problem, we want to draw the shear stress element, and we are done that, right? So this is really step 2. Step 3, we set up the rectangular coordinate system in which positive horizontal axis represents positive tensile normal stresses, and the positive vertical axis represents positive clockwise shear stresses. Thus, the planar create will be referred to as our sigma tau plane, shear stress plane. Normal and shear stress. So we're gonna draw step 2 or step 3 really. Our x-axis here is gonna be our sigma. Y-axis is our shear. Alright, plot our point. So in this case we want to do sigma x, and our shear xy is going to be our positive shear in this case, right? Positive xy to 10, and sigma x is going to be 20. So 20 KSI for our normal stresses, positive 10 KSI for our shear stress, and that gives us a point here. Then we want to do, as it says, sigma y tau yx. Sigma y in this case is 0, so it's going to be along our shear axis here. and it's going to be negative 10 ksi for tau yx. Let's put it around here. And we then go through step 5 is draw the line. So that's really step 5. Step 6. Now it's important to note that the line for the center of the Mohr circle at 0, the origin, well, where it crosses the origin of our sigma axis, that's going to be our sigma average. So we're going to plot that point, draw and label the extension of the line at this time. So we want to basically realize that the center of Mohr circle at O is the first plot point, sigma x tau xy. So this is actually what it's stating right there, is essentially that these are going to be, this line is representing our normal stresses, sigma x, sigma y. And that's going to be our sigma y value and sigma x value, right? So we had our 20 ksi. I guess I was kind of off on that one, but if we go down, that's our 20 ksi for this one. Sigma y on this one here is along that. So you can see, or I guess put, rather than sigma x, sigma y, I should say x-axis and y-axis. Really it's relative to the element itself. So the x-axis of the element, so as we rotate this, that x-axis will follow the normal face of that element, so it'll always project normal to that surface. So if we rotated that, this axis along, say, the Mohr's circle, as we rotate it, that's that normal to that face. That point along that line that you're drawing is essentially the normal stress coming off of that. So we'll see that here in a moment. So we've got that drawn in. And now it says basically we have our radius r and we have a and b. So yeah, it didn't tell us to draw a circle yet. So it says this is our radius, and we have our sides a and b here. And basically our r is just our square root of our sides, right? See, so it's r is equal to a plus b. And we go through and find r. And rather than punch this all in right now, I'm just going to work through it and just kind of go over how you go through this. And then we'll talk about the different situations. A is going to be this value right here along the base. So we want to take this and do sigma x minus our sigma average. This point right here is our sigma average. So the average point between our maximum and our minimum stress. So that's sigma av, and that's supposed to be a sigma. Alright, so we have that, and as we said, A is equal to sigma x, so our sigma x value that we had here, minus sigma average, and that gives us A. So our sigma average, we basically this whole value minus this, right? Sigma x minus sigma average, and B is just our shear tau xy right here. So B is tau xy, and A was this sigma average. I don't know why I wrote it over there. Run out of room over there. So that's our A and B. So we figure those out, plug those into here, find our radius, and from that, now we can draw our circle. See how successfully I can draw that. nice to have something for that. It's easier on your computer, I guess. If you're using Excel, you can actually get a program or something to do that. That's not too bad. Alright, so we have our circle. And now we go through, and it's talking about alpha angle. So the alpha angle it's talking about here is this alpha angle here. So we calculate that. So alpha, if we're using tangent, so your tangent alpha, for instance, is opposite over adjacent. Right, so it'd be B over A, and if we want to get that, we'd have to take the inverse of tan to the -1, B over A, and that would give us, so that's what they're getting there. Or you could use sine, so they're saying if you were using an angle up here, I guess, sine. Oh, I guess you could use the radius. Oh, that's what it's saying. So you're using this as just sine adjacent over your hypotenuse angle, or opposite over hypotenuse angle. So you could use that one as well. Just make sure you're using the correct angle and you have the correct sides. 8, we want to draw that complete circle, center at 0. So our 0 our average here, and a radius r is shown. So we basically draw that circle. Step 9 is sigma 1, we say is our maximum principal stress. So that's what crosses at when shear is 0. So when shear is 0, this is sigma 1. And we say sigma 2 is going to be our minimum. So that's really step 10. So it just basically says sigma 1 is going to be sigma average plus your radius. So we look for sigma 1, our maximum stress is going to be sigma average plus our radius r. And then for our minimum, it's going to be sigma 2 is the opposite. So we're origin here, average minus our radius gives us our minimum point. So sigma average minus our radius gives us that minimum point. And then our max shear, well, our max shear is just our radius because, right, if we wanted our max shear, that's right here, shear max. So our maximum amount of shear that we'll see at this stress element is going to be tau max, and that's equal to r. So at this point we have everything, and what they mention here, they want you to realize that the angles on Mohr's circle, and we haven't really solved for those yet, but this angle and this angle are twice that phi angle that we're going to rotate that element at. So we want to rotate the element to figure out how do we get to the max shear. So we're going to end up rotating our element counterclockwise by phi tau. So our angle to our shear would be clockwise in this direction. So we'd rotate this element clockwise to get to this maximum shear, and then our max shear would be this, and our average stress is going to be what we end up having off of each of our normal planes here. So as we see down here for max shear, we have max shear along our axis, so that's going to be tau max on each face, and then our sigma is our sigma average. So sigma average on all faces, tau is tau max on all faces. And then we have sigma 1 and sigma 2. If we wanted to get to our maximum principal stress in this case, so we're looking at this one, it would be, you rotate it to where shear is 0, and that's your maximum principal stress. So your max principal stress is going to be your phi theta. Yeah, or phi sigma rather. Mix those up tonight. So phi sigma gets us down to the sigma axis, and that's going to be our angle to phi sigma. And we want to divide whatever angle we get here by 2 in order to get us to the principal axis. And we see this because basically we know our x and y axis here are going to be 90 degrees apart. So typically, right, we draw our principal stress, we have our y axis, x axis. But if you notice, we have 180 degrees here. We have to divide that by 2 to get back to this element here. So that's where that half comes in, why we end up dividing by 2 to get this angle that we're rotating them at. So that's really where the 2 comes into play here. So up to this point, up to step 11, really this, I forgot to write sigma 2 here. This is really Mohr's circle. 1 through 11 is Mohr's circle. And then your 12 through 16 is drawing these stress elements. So drawing the stress elements, again, all I'm looking for in this case for the stress elements is we want to figure out these angles which are we're gonna rotate at, right? So as we see over here, we have an angle. This angle that we have is going to be equal to 2 times our phi sigma. So we want to find that angle, and to do that, we call this angle alpha, right? So we could say alpha is equal to that. So now we can look for phi sigma is equal to alpha divided by 2. And that's where they get, well, they don't really show it in here, but they have this equation here. So your alpha divided by 2 gives you your phi sigma. And then finding your other one, well, it's really phi to max shear, we want this angle, right? And this angle is going to be 2 times phi theta. So our shear angle. So our element needs to be rotated clockwise. In this case, it needed to be rotated counterclockwise. So that would give us, let's see, 90, so we have 90 degrees, right, minus alpha. Is that how they, what they really showed? Yeah, okay, that's how they end up getting. I guess I stepped ahead to 14. But so we have those two. So once we have those two, we can draw our stress elements. So I guess 13, before I stepped on to 14, I should have done 13, which is draw the principal stress. So our angle to principal stress here, in this case, we're going to rotate it. We have to use our stress element, and whatever our x-axis is that we used for our first point, so that sigma x value is going to be off of our x-axis, right? That's what we're using for our angle to find alpha. So that's what we want to make sure we're rotating from that point. So if our sigma x, for instance, is negative, it would be over on this side. We would be rotating back this way or back this way, right? So we'd be clockwise. In this case, we're counterclockwise, or rather vice versa, clockwise, counterclockwise. So we want to make sure we rotate that stress element. So we look at our stress element. We have our x-axis, our y-axis, our y-axis, our x-axis, and we're rotating this element by alpha, or half of alpha. And that'll be something, I'm just going to draw and kind of exaggeration here on what I would expect it to look like. So you get some sort of stress element like this. And your stress element that's coming off of this would be your sigma 1. And off of this other side, basically you're looking at, you've shifted this whole line and you twisted it to here now. So now we have sigma 1 off of our x-axis, off of this normal plane, and then sigma 2 is going to be off of this normal plane here. So we have sigma 2 in this direction, and that's actually, that's negative, right? So if that's negative, it's compression. So we end up getting, for strictly principal stresses, we'd get compression on sigma 2, tension sigma 1, and we'd be rotating this by this v sigma. And this is for maximum normal stress. That's our maximum normal stress element, and we want to do maximum shear. And this is our max shear stress element, and we're, in this case, to get to the max shear, we want to rotate counterclockwise to the max shear, right? So draw our x and y axis in the orientation that we initially would have pulled it off of, say, the machine, right? And then we want to rotate the stress element by this angle that we found, or really half of this angle, right? And again, that would be your, you can use 90 minus alpha to get to that. And you're rotating it, again, kind of exaggerate, because I'm not sure what the angle would be at this point. And in this case, we would have, so we've rotated this element again, and now we have, off of one normal face, we'll have a max, well, we'll have a max shear in this case, but we'll have an average, right? So actually, off of each sigma x and sigma y, or really off of our normal stresses and perpendicular to our planes here, normal to those planes, we would see that it would be a sigma average. So our maximum shear stress angle puts us at a sigma average normal stress. It's all sigma average. And our shear is positive, right? And again, positive shear clockwise, so it's opposite of right hand rule. And along this face that we rotated, this angle that we had for phi theta is going to give us our positive, so we want this to be positive. It has to rotate clockwise. Clockwise. And then the other face has to counteract that, so that's where we get our negative shear along this face. So this is positive shear shear max, and this is going to be our negative shear max to counteract that positive shear max. All right, and that's really how you would go through and solve the Mohr circle problem. Now, our third principal stress here that we didn't really talk about, and they get into a little bit after the fact, but again, this is what I was looking for the homework, just the 2D, since we didn't really cover three-dimensional. The second problem kind of does cover three-dimensional because it changes your maximum shear. Your other minimum and it kind of affects your minimum stress as well, because your minimum stress of 0 is less than. I'll look. We'll talk about it here in a minute. But basically, this is what I'd be looking for your problem. I wanted you to draw the circle. I wanted you to show your stress elements, show your work on how you got there. I kind of did a generalized version, but I was seeing everybody was doing the first one rather well, except for a few screw ups on the normal stress and maximum shear stress angles and how to apply those to your stress elements. So please look over the stress element drawings, especially on the first one. The second one, again, deals a little bit with that third principal stress. And in this case, for this problem, it was 0. And a lot of times you'll see another circle they'll use, and they'll put in circle because really that 0 point sigma 3 is in between our minimum and maximum. So what they show, they talk a little bit about this over here, where you start seeing that you have 3 stresses, right? Really, if you look at a three-dimensional, in the real world, you have 3 dimensions. So we saw in the very beginning that they had that 3-dimensional cube, and from that is you would add that third dimension for sigma x, and you would get this sigma 1, sigma 2, and sigma 3 value. And essentially, you end up doing for those is you would rate them. Sigma 1 is the highest, sigma 3 is the smallest, sigma 2 is the middle. So if we were to really change this to add that third circle, we would have to change sigma 2 and sigma 3. So we won't necessarily do that for this problem, since we're not going to show this in like 3 dimensions here. The second problem, you will have to think of this a little bit, because in our second problem that we did, I believe I gave you 29. Been a while since I looked at the homework, but if you have, say, two negatives, so negative x and negative y, your Mohr's circle, just in general, will draw your max shear angle and your normal stress axis there, so you get your 2 axes. And we go through and start drawing this one out. We would see, well, if we have negative 840 kilopascals, we have also a negative shear of 120 kPa. We would end up, so this is 29, we'd end up going negative, what did I say, 840 kPa, then minus 120 kPa, right on our minus 120 kPa. That gives us the one side. The opposite side of that circle is negative 335. I should have drawn this a little bit bigger. Negative 335 kPa. And then it would be a positive 120 kPa from there. So those are your 2 sides of your circle, right? And you draw your axis. And in this case, because we had our negative on our x-axis, and this was our y-axis, we now have to draw the circle and think about our rotation differently for our angles on our stress elements. Okay, we can draw the circle. And I don't think, actually, it's not going to cross. This is where my drawing is not going to be correct necessarily as far as dimensions. But what you would end up seeing is, since our average and our radius is like that, you're not going to end up crossing that 0 axis. And again, I should have give myself a little more room. Draw the axis over here a little bit further. We had 120 there, 120 there. All right, so that would give us our circle. We end up having, in this case, sigma 1, and our middle is in there. Our average, stress average, we do the normal is there, and we end up having basically our sigma max is here. And if we think about that other axis of our stress element in the z-axis, so if we're thinking in 3 dimensions here, that z-axis has 0 stress on it. So really our minimum, or well, technically I guess our maximum is going to be 0. Right? So we have this other circle which is going to change the max shear. So now this circle here ends up being, so you end up getting a circle that's, again, if I had some software or something to draw this with, it might look a little better. You get something like that. And now our max shear that we look at, so a max point that we come to on here is going to be higher than if we weren't thinking of that third axis. So we have to think of that axis even if it is 0 in this case. So you would end up getting sigma 2 would be our center. So if we're doing a 3-dimensional, and sigma 3, it's like that. In this case, we would still use our minimum, maximum, and then our stress elements. We would still end up pulling off of this circle for our 2D case. But when you look in the answer key for that, or the back of the book, which 29 is odd, so it's in the back, you would see that if you thought this was our minimum stress here, or maximum rather, due to this being more negative, you would have seen that it was actually 0, and you would probably be wondering why. It's due to this reason here, because that third principal axis has a 0 point, so you end up having to think about that as your minimum, or in this case the maximum stress that you end up having. So that's really the problem you end up seeing with the second one. But as far as everything else is concerned, you still work through it the same way. Your angles are found in the same way. So getting up to maximum, you would basically, it would be that angle to get to your 90 along the max here. So it would still be your angle here. This would still be your angle for alpha. So this would be your angle for your max shear. This would be your angle for alpha there, and you would still be using this axis here as your rotational axis to show that stress element rotation. So you would still have your typical stress element with sigma y, sigma x from the beginning of the problem. In this case, they were both negative, so actually they're both compression, right? And then you would go through and show your rotations, and in this case we would see that actually we'd go off of, sorry, I put the alpha angle there. If you remember, we put the x-axis off this side, so really the alpha angle is to our sigma axis. So the max angle to sigma is that phi sigma, or really 2 times phi sigma, right? And then to get to our max shear is that opposite angle. So this one's our 2 times phi shear. And you would have to use that first point to really figure out which way do I rotate this. So in this case, we would rotate to max shear in the counterclockwise direction, and we would rotate to our max normal stresses in the clockwise rotation. So that's really the two problems. Hopefully that helps explain it a little bit better. Again, if you're having trouble, please let me know. Shoot me an email, and we can go over the problem together, either in lab or after lab. We tend to have a lot of time after lab, so please take advantage of that. Otherwise, yeah, I guess I'll see you guys next lab. Bye.